As a non-sequential ray trace program, ASAP offers various tools for polarization analysis. With the advent of ASAP 2008, a number of exciting new features extend this capability dramatically. There are new polarization device types, new source polarization controls, including randomization, and new analysis tools, including a Poincare sphere visualization tool in the 3D viewer. And now I'll demonstrate a few of these features. So now we're in ASAP and we're ready to look at a few examples of the new polarization support. By way of introduction, you're going to see a lot of Maltese cross patterns, but you'll see many variations of them. But this is one of the hallmarks of a well-built polarization code. So first, let's look at a simple perfect lens with two polarizers crossed and see what we get. Just to give you a basic introduction to the system, we have a horizontal polarizer, we have a vertical polarizer, and between them we have a lens. It's actually very hard to see here. And we have a detector at the end. And we see the classic Maltese cross pattern. And that's a spatial Maltese cross. We often see also directional Maltese crosses or iconoscopy images. But this kind of pattern is going to show up in variations in several of the examples we're going to look at. In the next example, we're going to have a real lens, not a perfect lens, which is an ideal planar lens-like object. This lens has real structure and thickness. And you see it here in the 2D plot window. It's between two polarizers as before, and we have a plane on the right, which is the detector on which we're going to collect the energy. So again, we have the Maltese cross pattern on the detector, and we have the real figured lens, a fairly fast lens with a moderately high NA, and one hallmark of a good polarization trace code is the ability to produce a pattern like this. One of the features of this new polarization code is that a polarization device can wrap around a non-planar surface. In the previous two examples, our polarizers are planar polarizers, but in this case, we've taken a crossed cylinder lens and placed crossed polarizers on the crossed cylinders. I'll show you this in 3D to make it more clear. So you see here, we have a cylindrical lens backed up to a cylindrical lens that crosses it, and we've wrapped polarizers around those two surfaces. And now if we take a look right behind the detector, we see a pattern, and then as we go further away from the optical system, we see a variation on the Maltese cross that is very skew because of that conformal nature in the two polarizing surfaces. So this is an example of a fairly sophisticated non-planar polarizer system. So let's look at another conformal optic example. This is an example of a quarter wave plate conformally coated on an optical dome structure. The input polarization is linear. The output polarization is modulated by the quarter wave plate, which was conformally coated on the outside of the dome. So along the axis, both cross axes, we have linear polarization. And as we go away from those axes, we pass into elliptical states, which vary in ellipticity depending on exactly where we are. So now let's examine another new feature and introduce source randomization to this problem. So we have a conformally coated dome with quarter wave plate, but we have randomized polarization going in. So it's very similar, but in this case, the input polarization is not perfectly linear. There's a slight ellipticity and a slight orientational variation. This is a new feature of sources in ASAP and their polarization support. So we'll see some minor perturbations in the output due to the perturbations in the input. And this is a useful way of simulating non-idealities in a system in the polarization of the source itself. Not only can we simulate a single polarization element, such as a polarizer or wave plate, but we can cascade multiple elements into a single cascaded element. So in this case, we have a simple isolator formed using a quarter wave plate and a linear polarizer, and we're going to look at the light that passes through it. So we have a cascaded element, which is a unidirectional isolator, and we have a point source beaming through it, and it's off-axis. So at this mirror on the right edge, we have stopped the light, and we see that it looks like a point source off-axis. The light has passed through, and it doesn't look as if we've changed anything about the light yet, but of course we have changed the polarization state. Now if I allow the light to pass back through the isolator, we see that, again, in a variation of the Maltese cross, we have some maxima in passage back through the system, but we also have some very low energy zones where the isolator has functioned as an isolator. Note that at the peak we're at a fairly low level relative to the initial level, but in the central part we're at a very low energy, very near zero. So since we've talked a little bit about randomization of polarization, let's look at a few examples of how that randomization works. First, we'll take a quick overview. In this case, we are randomizing in each of three ways. So let's just take a look at them in turn. This is a randomization in both direction and in ellipticity. Just so that it is a little more clear what we're looking at, let's take a look at each of those randomizations separately. So here is a randomization in orientation only without the variation in ellipticity. So we see that only the reference direction of polarization is changing. In this case, we have kept the reference direction of polarization across the window, and we have merely changed the ellipticity of the rays, or of the polarization. So while we're thinking about randomization of polarization, let's use a couple of the individual randomization examples to look at another new feature, an enhancement to the list rays command. Using the orientation example, you see we have orientational randomization of the source. Let's take a look at list rays. List rays has been enhanced with a polarization subcommand and a Stokes option, and that means that we output with the list rays the polarization information in Stokes format. So in this case we have the reference polarization direction as a 3-vector and the Stokes parameters. Let's look at the ellipticity randomization example to look at another form of the list rays polarization using Jones vectors. So we have our ellipticity variation, and if we take a look at this list rays output, we see that it's asking for Jones format. And if we scroll over, we see again the reference polarization direction as a 3-vector, and then the real and imaginary Jones components in the reference direction and in the direction that is normal to the reference direction and normal to the ray vector or the propagation direction. So now let's take a look at another new source feature. We now have the ability to dump a source file, including polarization information, and reload that source. In this case, I'm going to make twin sources by tracing a single source, capturing that using the dump command with polarization, and then load that polarization field back in twice with slight offset between them to see what twin sources with a lateral offset would do. So here we see a Maltese cross, but because of the offset between two sources, we see a very strong null in one direction and an incomplete null, truly a null that doesn't go all the way to 0, in the other direction. Let's look at another example of that phenomena that makes that a little bit more interesting. In this case, we've used a somewhat slower lens, so the cone is somewhat smaller in angle. We've given ourselves a little bit more room to work between the polarizer, detector, second polarizer, and second detector. So we're stopping this beam at the place where the rays are stopping now and recording that, and then creating 2 copies to propagate the rest of the way through the system. In a complex system, this would allow us to save the ray trace time for one of the sources going through the system. And now you see the twins, and as a result, you see 2 offset Maltese crosses that form a very interesting interlacing ring pattern. While we're having fun with dumping polarization fields and bringing them back in, let's look at an axial example of this offset. So instead of a lateral offset of the 2 polarization fields and propagation to a final plane, we're going to do an axial offset. So now we see the first source and the second one, which is further along on the optical axis. And we see, again, 2 rings, 2 Maltese cross patterns that obviously have a different scale, but now they're concentric because they were displaced axially rather than laterally. And let's now look at a combination of axial twinning and a little bit of twist, just a degree of twist between the 2 patterns. So remember, we're tracing one source, then duplicating it using a dump command, and then bringing it back using an emitting data command. And so one trace through the optical system allows us to look at the overlap of 2 polarization fields with this process. This will look similar to the previous case because you can't see 1 degree of offset in the ray trace. But in the final result, we see a very different matter. Instead of having clear Maltese crosses in each direction, we have weakened maxima around the edges and because of the offset in opposite angles, the strong sides of the pattern, or the strong diagonals, are opposite. So now let's take a look at one final and truly wonderful polarization visualization tool. In the script that you see, I've dumped in Jones format the ray set in my system, and I would like to view it. So I just open it in the 3D viewer like any distribution in ASAP, but now the viewer understands that polarization in Jones format can be turned into a Poincare sphere. In the Poincare sphere that we see here, we have right circular polarization at the top, left circular at the bottom. The equator represents linear states with different orientations, and each point, therefore, represents the polarization state of one ray. The color of each point represents the flux of that ray. So you see that we have, for instance, these blue rays have fluxes that are approaching 2. The fluxes that are white are very low, or relatively low fluxes, and if we'd like to see those plotted more carefully, more finely grained in color, because they're very low, we can go to logarithmic and cut off the high values, which are the values near the poles. So if I apply that, then I see those points are now colored, and I can make a distinction in flux among them. And just to give you a little bit more background on what this can give you, let's take a look at one point. We can select a point, and it tells us its index in the distribution file, its flux, its wavelength, its position in position space, its direction cosines, and its polarization data. So we have the polarization reference orientation, and in this case, the Stokes vectors, which are the vectors that are being plotted on the surface of the Poincare sphere. So this has been a brief introduction to some of the great new features for polarization, ray tracing, and analysis in ASAP 2008. We hope you find it useful, and we look forward to hearing your feedback.